All right. Welcome to Unit 2, Lesson 21, or Lesson 21, as they say. All right, the first thing I want you to do is to hit pause and get the learning targets onto your notes. So either that's copying it to the notes that you printed off, or if you're just working on plain paper, that's fine. Get the learning targets there, and let's just hit pause for a minute and get that done. Okay, so what we're going to do here is we're going to move into two variable inequalities, right? So you were solving 3x is less than 12 and you were able to deal with that. But now we're going to start bringing in two variables, so x and y, all right? And you're going to be determined which side of the line has the solutions, right? And you're going to be able to describe the graph that represents the solutions in a linear inequality of two variables. All right, let's get moving. So first and foremost, I think if you're working on plain paper, hey, what should I be copying down? I would copy down this expression and then something like decide if the values are less than, greater than, or equal to 12, right? And then I would copy down all of the values. But more importantly, how do we decide? Well, we have values of x and we have values of y, and we're going to substitute those in for x and y here. So 2 times 0 plus 3 times 5 is going to be equal to 0 plus 15. And even I can do that one. That's 15. And the question is it less than, greater than, or equal to 12? So 15 is greater than 12. All right, that's our first answer. Next one we have up, I already kind of pre-wrote it, right? So 6 is our x, 0 is our y. So 2 times 6 plus 3 times 0 is going to give us 12 plus 0, which is 12, which is equal to 12. At this point, I think you should press pause, do the last two, right? Do these two on your own, make a decision, and then unpause and check your answers against mine. Press pause now. No peeking. Especially you, Shack Joe. Okay, so for the second to the last one, once you substitute -1, -1 in, I get a -5, which is less than 12. And for -5, 10, I got 20, because 2 times -5 is -10. When you add that to 30, you get 20, which is greater than 12. How did you do? How about you, Damien? How did you do? Our next mission, should you choose to accept it, and you will choose to accept it, we're going to try to find, right? We're going to find some coordinate pairs that represent solutions to the inequality. So down here, there's some inequalities, like x is greater than or equal to y, and -2y is greater than or equal to 4, okay? So we're going to find some coordinate pairs that represent solutions. We're going to place sets of these both versions, right? So some that do and some that don't. We're going to use, I'm going to go with the 2 different color or 2 different symbols. So maybe we should go with the 2 different colors. And then we're going to plot enough points till you start to see a region that contains the solutions. And we're going to look for a pattern describing the region. So what I've established here on the left side, right, is a system. Green dot is going to be that it works, right? Good to go. And the red dot is going to be that it doesn't work. Not good to go. So let's start with something positive, right? So let's start with this idea over here. Who is this? This is the coordinate 4, -2. And the x value there is certainly greater than the y value, right? It's not equal to, but it's definitely greater than y. So that satisfies that idea. How about another one? Let's go way up here and let's identify who that is. That's 8, 7. So that is a good point, right? X is greater than or equal to y. And what if we went up one more, right? Who's this? This is 8, 8. So that's still good to go. X is equal to y. That's okay. But now what if we chose a point way up here? And who is that? Well, that is 4, on the x-axis, and it looks like 10 on the y-axis. So 410 does not meet the criteria of x being greater than or equal to y. X is less than y, so that's no good. All right, well, let's see here. What if we went to, say, 5, 6? Again, 5, 6, x is smaller than the y value, no good. But then, if we just move down just a smidge, and I know what you're thinking, Harrison, you're thinking, Mr. Brecklin, how about 5, 5? 5, 5, good to go. 6, 6, good to go. 7, 7, good to go. 0, 0, good to go. How about you, Skylar? What are you thinking? You're thinking, Mr. Brecklin, give it a shot. Go into uncharted territory. How about -4, -4? Those are the same. So wouldn't that be x equals y at -4, -4? Well, it certainly is. And it looks like that we're sort of making our way down this line here. There seems to be this boundary line. And I think that maybe we might be starting to develop a pattern. How about up in the upper left-hand corner over here? This is -8, 6, right? Where x is certainly less than y, right? -8 is less than +6. And then what about down here? That's an x of -8 and a y of -5. So even though y is negative, -5 is still greater than -8, right? Think about that whole horizontal number line. Left is less. -8 is certainly further to the left than -5 is in terms of value. So the x value of -8 is less than -5. Does not satisfy this requirement. And one last one, just to beat this all the way into the ground. What about 1, -4? 1, -4. Well, 1's positive and -4 is negative. So x is certainly greater than or equal to y. I think that any point from below that line where all the values are identical works. Something to be said there. Let's give another one of these a shot. Okay, so now we're looking at -2y greater than or equal to -4. So I'm going to write that over here. -2y greater than or equal to -4. Now, I'm not a fan. This one's going to be harder to negotiate. So for me, I think I'd like to kind of get y by itself. And so the first thing I'm going to want to do is get rid of that -2. But remember, as soon as I divide by that negative, I like to remind myself to flip that sign, and then I'll continue along the path of solving this inequality. The -2's cancel out to be a +1y, and -4 divided by a -2 is a +2. So now what I'm looking for are all y values that are less than or equal to +2. So I think what might be a good idea is if I just snap the line right along the value of 2. And where are all the y values less than or equal to 2? Oh, right here. This is -8, -4. But I'm only focused on the y value. -4 is certainly less than 2. And the original piece, -2 times -4, was supposed to be greater than or equal to -4, which is +8 is greater than or equal to -4. So that works in my original function. Kind of just makes me feel reassured that I've rewritten, re-expressed that correctly. And let's see here. Oops, I guess I varied from my color rule, huh? So I guess red dots will be okay, and I'll use purple dots for doesn't work or not okay. So I'm going to pick a point over here, and that has a y value equal to 6, and 6 is not less than 2, right? No dice. How about a point over here? What's this y value correspond to? That corresponds to a y value of 3, and 3 is not less than 2, so no dice. If I come back below the line and I go to say, oh, I don't know, -4, right? This is a y value of -4. Technically 4, -4, but I'm just paying attention to the y value, and -4 is certainly less than or equal to 2. So it looks like all this region down there seems to satisfy my query. Now, just another brief announcement, sidebar. If you don't have the full grid, just making a little half grid, sort of like a little quick grid like this might be enough, and just plotting some points and kind of going along with me and labeling them. But I don't think, if you're drawing on blank paper, I don't think it's necessary to have every last living grid line in there, okay? Just a sidebar note. Okay. So hopefully at some point you're starting to see, well, wow, we keep talking about this idea of, maybe there's a line here and down here works, or up here works, or maybe there's a line here and above here works, but down here doesn't work. Or maybe the line's going to be like this, right? And down here works, but up here does not work. Okay, so it's this idea of lines. So not to get too ahead of ourselves, but just want to kind of throw that idea out there that there's some line here that crosses over to where we go from, and I'm going to try to go back to my original, when we go from the no-go zone to the go zone, all right? So let's just pick a point, shall we? And so I'm just going to pick a point right here. And what do I know about that point? I know that that's 2, 4. And so when I take that and I do 2 plus 4, it's supposed to be bigger than 10. Is 6 bigger than 10? No, it's not. So that's a no-go point. Well, how about over here? This is going to be -7 and -5. Okay, so -7, -5 on the y. And so what's -7 plus -5? That's going to be -12. Is -12 bigger than 10? Absolutely not. Well, how about if we go way over here? And that looks like that gives us a 9, -6. And what do we have there? If we add those together, we're going to get 3. Is 3 greater than 10? No. And so now you say, well, where the heck are these things? Well, let's pick something way over here. And we have 8, 9. And when we add 8 plus 9, we get 17, which is definitely bigger than 10. Good, good. So now we come back over. So what if we go over in the corner here? This looks like it's going to be -8, 9. When you add those together, you get 1. Bigger than 10? I don't think so. Back over to the go zone. How about 5, 10? 5, 10 adds up to 15, which is bigger than 10. Yes. So it looks like maybe this area, but not exactly sure where that line is. But I think I could re-express this, right? If this was an equals, could we re-express that? Take a look at it on Desmos and maybe see how this pattern is evolving? You bet your bottom dollar we can. Hold on to your hats, Matt and Devin, or I should say your hoodie tops. Okay, let's move on. Okay, so what I did is I did this really slow and methodically, and I made the little asterisks perfectly, just like that, so that you guys could take a better look at these 4 problems, right? And we did 3 of them. And I know what you're thinking, Emelina. You did that by hand? No, come on. So there was that line, right, that boundary mark, where these were the no-goes and these were the goes. And then we did the second one together, and we said, hey, there was a sort of this horizontal line, and there was the no-goes, and there's where the goes. We skipped the next one, but just to draw in the boundary line, it was a vertical, and here was the no-goes, and here was the goes. So just for the record, when I see x's and y's, looks like we got diagonal lines. When I see just a y, I have just a horizontal line. Remember, y equals a number is a horizontal line, and x equals a number is a vertical line. And then we have x and y again, and we have this diagonal set up over here. And it looks like we got our goes above on the top and the no-goes on the bottom, just like we had experienced. So this was our first, second, and third example that we just did, but just a little better version. So hopefully you can see it a little more clearly. So next we have a graph that represents the solutions to an equation. Now remember, the solutions to an equation are just the points that are on the line, right? To be a solution of an equation means it's all the points that are on the line. Okay, so now what you really want to make sure you have in your notes is how to re-express this equation in slope-intercept form. So to be able to get to slope-intercept form is a critical skill that you'll need forever and ever. I mean, sometimes I've gone to buy ski tickets and they said, hey, if you can rearrange this in slope-intercept form, we'll give you a 10% discount. I said, no problem. I'm a high school math teacher. No, Kyle, that didn't really happen. All right, just kidding. So slope-intercept form, let's get back to business here. All right, first thing I did, is I subtracted x from both sides. So please work along with me. I think that you should try to copy this in the slope-intercept form on your own and then look at the screen. Press pause and see if you could do that. Seriously, press pause and try to get this into slope-intercept form on your own. Okay, so I subtracted x on both sides. Then I had negative y, right, was equal to 5 minus x, but I don't want negative y. I want positive y. So I divided by negative 1. Don't forget that that negative is negative 1 sitting right there. So I divided by negative 1 across the board. Remember, everybody on the left and everybody on the right. And I'm left with positive 1y. Those cancel out to be positive 1. 5 divided by negative 1 is, whoops, I have a mistake here myself, negative 5. Negative 5. Whoa, that was close. Gives me a negative 5, and then I divide a negative x divided by negative 1, I get a positive 1. So I come over to my graph here, and what do I notice? That's my slope, or my y-intercept. And if I go up 1 over 1, up 1 over 1, up 1 over 1 5 times, I'll land at 5, 0. And then we have enough to snap a nice straight line. Okay, that's critical. If you can understand that, then you're going to understand this super, super, super easy, right? Let's try to re-express this in slope-intercept form. So we start by subtracting x on both sides. And what do we get? Negative y is less than 5 minus x. And now we're going to divide by what? Negative 1. Whoa, hit the brakes there, pal. Flip the sign. Continue on the journey. And what do we get? Y is greater than negative 5 plus x. So what does that look like? It looks like the same 2 points, right? I know that those are going to be the same 2 points because it's the same line, but it's not a solid line. Why not? Because this is a strictly less than, right? So just like on the number line where we used an open sign, now instead we're going to use a dotted line. So we use a dotted line. And now we're looking for where are all of the y values greater than this value. Well, when I think about y values being greater, I think about going up. All the y values up here are greater than the y values down here. So all of this region is going to be my success region. Now, how can you check this? Well, let's hit pause for a second. And check it out, my algebra peeps. Whoa, Mr. Brecklin, that looks like it's from Desmos. You betcha, Megan. I got Desmos on my iPad, took a little snapshot, brought this into reality just for you guys. Why? Because I care. Notice line is dotted line. Dotted line goes with strictly less than, strictly greater than. Solid line is going to go with strictly greater than or equal to or strictly less than or equal to, right? If I see a solid line, I'm going to make a solid line. Otherwise, I make me a dotted line. And then y's are greater than, notice where the shaded region is. So just for the record, let's pick and check a spot. Now you know who my favorite spot is going to be. You bet you the origin, right? The origin is the easiest place to check. Why? Because it's 0, 0. Is 0 greater than negative 5 plus 0? Is 0 greater than negative 5? Yes. So this is in the region or on the correct side of the line. The origin, I don't use the origin when it's on the line, but as long as the origin's on one side of the line or the other, right? So if I check the origin and I get a true statement, I shade where the origin is. If I check the origin and it's not, I don't check. I don't shade that region. All right? So just What am I signifying by shading this region? What I'm saying is that any point in this area, be it right here or right here or right here or right here or right here, is part of the solution set. How about a point that's on the line? No. Dotted means, remember, not included. But more of that to come in the future. Let's go back to our original graphs. So here we are, back to my original. Is that as good as Desmos? No, but is it correct? You bet your bottom dollar. All right, so let's go back here and let's put our two dots here again. I see a less than or equal to, I see a line, so I'm going to draw a line. And I know that I can write y, and I know that sign's going to flip-flop greater than or equal to -5 plus x. I don't have to keep redoing the algebra. I know what it looks like. I know that the sign flip-flops. I know that I got -5 plus x on one side. I know that I got y on the other side. Where are all the y values greater? Over here. So what's the difference between these two pictures? Dotted line, solid line. All of the points on this line are included in the solution set. All of the points on this line are not included in the solution set. So this y-intercept, not part of the solution set. This y-intercept is part of the solution set. How about down at the bottom here? This is going to be y, -5 plus x. I know my sign flip-flops, so that's y is less than. I draw the line, right? Okay, I'm going to exaggerate. It goes through -5 and 5. I know that part. Where are all the y values less? Less is lower for y's, so below the line. Whoa, whoa, whoa. I thought you said strictly less than is dotted. Yes. So let's make that a dotted line. Now, I go back over to my last one. I'm going to connect my dots. Solid line because I see one. Y is over here, -5 plus x over here. I'm going to flip-flop that sign, I know, because at some point I had to divide by -1. Boom, boom. The y's are less than down here. So again, what's the difference? All the points on the line are included. So any point on this line is also going to make this statement correct. Any points on this line would make this statement incorrect. So the points on that line are not included. But any point down in this region here or any point down in this region here would make both of these correct statements or true statements. Remember, what does it mean to be a solution? It means it makes the statement true, right? A pair of x, y coordinates, right? In two variables, there's two variables, x and y, that make the statement true. Your homework previous to this was single variable. You were solving 3x less than or equal to 12 type stuff, right? 5y is greater than 15, right? These were singular variables. Now we have two variables. Take a breath. All right. Let's keep moving on. Are you ready, Natalie? Yes. Okay. Okay. So first off, just a little bit of review. Let's keep in mind that vertical lines and verticals go up and down, right? So vertical lines are defined as x equals a. Horizontal lines, right? Horizontal lines move left and right. I always think about that with that horizontal line in H. Horizontal lines are defined as y equals a, where a is just some value, right? So here I see that this is a vertical line. And what is the value that it goes through? Looks like it goes through 3. So I think 3 is a good argument. Whoops. So if indeed that value is 3, and that's a vertical line, then I guess the inequality, right? So first let's think about it as an equation. That would be a vertical line equal to 3 if that was an equation, but since it's an inequality, I have x and I have 3. Now the question is, it's dotted, right? So I know that dotted is greater than or strictly greater than or strictly less than, I should say, or strictly greater than. Which one is it? Well, it looks like the solution set are all of the values to the right. I know that left is less, so I guess that's all the values where x is greater than 3. What do we have over here? We have a horizontal line. So I know this is going to be y and some number. What does that number appear to be? I drew right through it, but it looks like it's a -2. And it looks like we shaded below. So when we go down, that's less. So y is less than 2. That's a solid line, so I guess we're going to include the equals. So that's going to be y is less than or equal to 2. Okay, so now it's getting more difficult. And this is why I saved the last couple of names for the end. The heavy hitters. Amelia, are you ready? Of course I'm ready, Mr. Brecklin. And what do you notice about this picture? Well, you say, well, I notice that the y-intercept is 0. So if this were an equation, that would be y equals mx plus b, right? And so an equation, it would be y plus 0. And then we can count from 0 up and over to another point. And it looks like we go up 2 and over 2, right? Which is y equals 1x, or y just equals x, because plus 0 is plus 0. So I know that this is what the equation would look like, but this is an inequality, and it's a dotted line. So I know it's y, I know it's x, I know it's less than, or I know it's greater than. The upper region is shaded, so that's all when the y values are greater, right? Up is greater than, down is less than for y. Left is less for x, right is greater. But these aren't distinguishable by absolute left or absolute right. But there still is sort of an above area and a below area. Okay, so that's y greater than x. Well, if it's y and x, when it goes through the origin, right, this is still a y equals x plus 0. How do I know? Because it's still up 2 over 2. So it's essentially the same thing. So we're still a y and an x, but this is a solid line this time. So I know it's strictly less than or equal to, or strictly greater than or equal to all of the values below the line, so I guess the y's are less than or equal to x. So these are our inequalities for C and D. Alrighty. Again, if you're doing this by hand, you should have some sort of rough sketch. If I were doing this on blank paper, then I probably would have had this in my notes, and then y is less than or equal to x. Okay, just for a little ha-ha example. And that about does it for this section. So you've taken down a lot of information. Again, Desmos is going to be my friend, right? Lean on Desmos to help you figure things out. But in wrapping this up, the equation, because it has an equal sign, x plus y is an equation in 2 variables. Why do I say that? Because there's 2 variables, silly. And a solution is any pair x and y whose sum is 7, or that is, any point that's on this line is a solution, right? And we can represent the solution by drawing a line. I think if I was writing some hand notes, I would just make sure that I have the equation. The idea of a solution is any pair whose sum is 7, and then I would also say that the solution is all of the points, or I should say are all of the points on the line. I would have that and this part in my hand notes if I'm just copying. If not, if I have this printout, I'm highlighting that section. Now, the only difference between the equation and the inequality is whether or not it has or has the absence of an equality. If it doesn't have an equal sign, then it's an inequality, right? If it's not an equals, it's inequality, not equals, right? And this is in 2 variables. How do I know? Again, because x and y are on the scene. What's a solution? Any pair whose sum is less than 7. So all of the points down here, like -6 plus 0, less than 7. -4 plus -7 is -3. It's less than 7. And now this is or equals 2, right? So 5, 2, that's exactly 7. 0, 7, that's exactly 7, right? So anything that's adds up to or includes the value of 7 would be a solution. And what would make it false is if it's greater than 7. Like take this solution right here, 8, 8. If you added 8 and 8, you'd get 16. 16 is certainly not less than or equal to 7. So this is in the no-go zone. And lastly, the idea of the absolute less than 7, right? The only difference between this and our last picture is the dotted line. So none of the points on the line work, only down here, right? These are below the line, but 0, 7 right here no longer works. Why? Because 7 is not less than 7, it's equal to it. So all the points on the line would make a false statement. They would not be part of the solution set. So the last point of business for you is to decide which of these graphs represent 2x is greater than y, right? So this would be your this is the cool down. You can do it. All right, enough of that. Come on, man. That was lame. Sorry. Let's get back to serious business here. Which of these graphs represents 2x greater than y? Now, the line represents y equals 2x. So I suppose if I had 2x greater than y, perhaps I could rearrange that from left to right. Like if I put the y here and the 2x here, which way does the inequality go? Could I put it in Desmos? Could I help myself out? Could I pick a point over here, right? Could I pick a point and see which one is actually the story, right? And so here's what I might recommend. I'd probably pick the same point maybe, right? And just keep going with that one. And decide, well, is that point a point that makes the statement true? Or is it a point that makes it false? Now I could go with the Desmos deal, right? I could go with the Desmos deal, and I could try to rephrase this in terms of an inequality that I could put into Desmos and check it out, right? That's one way. It's kind of half cheating, right? I could just check to see if those points work. And if this point works, is that the graph? Well, this point is the same point, and they're both the same shaded region. And what's the deal? Oh, this is dotted. This is solid. I'm going to post this warm-up in Google Classroom, and you're going to select your answer there. And that's how I'm going to know that you know what's going on. All right? So there you go. That's one full lesson 21 coming your way. Enjoy. Hope you got some giggles out of it and that you learned something. Okay. Thanks for coming, and answer the warm-up on the Google Classroom. It'll be an assessment's one-answer question.